For millennia, humanity has gazed at the stars, pondering our place in the vast cosmic tapestry. We've sought to understand the laws governing the motion of planets, the birth and death of stars, and the expansion of the universe itself. Yet, hidden within this grand cosmic dance lies another realm, equally profound and even more mysterious, the quantum world. This is the realm of atoms and the particles within them, a microscopic domain where the rules of classical physics, the physics of our everyday experience, break down. Here, intuition falters as we encounter a reality where particles can be in multiple states at once, where matter behaves like waves, and where uncertainty reigns supreme. This is the realm of quantum mechanics, a revolutionary theory that has profoundly altered our understanding of the universe. It's a theory that challenges our classical intuitions, revealing a world stranger and more wondrous than we could have ever imagined. Join us as we embark on a journey into this mind-bending realm, exploring the mysteries of the quantum world and their implications for our understanding of reality itself. In the early 20th century, physics underwent a seismic shift. The comfortable certainties of the past were about to be upended by a series of revolutionary discoveries. The old, comfortable world of classical physics, where objects moved in predictable trajectories and energy flowed continuously, was shaken to its core by a series of groundbreaking experiments. These experiments challenged the very foundations of what scientists thought they knew. These experiments revealed that the microscopic world, the world of atoms and their constituents, danced to a different tune, a tune governed by the bizarre and counterintuitive laws of quantum mechanics. This new physics was unlike anything that had come before. Classical physics, with its deterministic laws, had served us well in describing the macroscopic world. It explained why apples fall from trees, why planets orbit stars, and how engines power our cars. These laws provided a sense of order and predictability to the universe. However, when scientists began to probe the atom, they encountered phenomena that classical physics simply couldn't explain. The deeper they delved, the more they realized that the rules governing the microscopic world were fundamentally different. Atoms, once thought to be indivisible, were found to be composed of even smaller particles, electrons orbiting a nucleus of protons and neutrons. This discovery was just the beginning of a journey into the strange and mysterious world of quantum mechanics. But these particles didn't behave like miniature billiard balls, as classical physics would suggest. Instead, they exhibited wave-particle duality, existing as both particles and waves, depending on how they were observed. Instead, their behavior was governed by a strange set of rules that defied common sense. Particles could be in multiple places at once, and their properties were not determined until they were measured. Quantum mechanics emerged as a radical departure from classical physics, a revolutionary framework that embraced uncertainty and probability at its core. It was a theory that required scientists to rethink their understanding of reality itself. It was a revolution that would not only reshape our understanding of the atom, but also pave the way for groundbreaking technologies and challenge our very conception of reality. From quantum computing to advanced medical imaging, the implications of quantum mechanics continue to unfold, revealing a world far stranger and more fascinating than we ever imagined. One of the most mind-boggling concepts at the heart of quantum mechanics is superposition. Unlike classical objects, which exist in a single, well-defined state at any given time, quantum particles can exist in multiple states simultaneously. It's like a coin that can be both heads and tails at the same time, a concept that seems paradoxical from our everyday perspective. Imagine a single electron orbiting an atom's nucleus. According to classical physics, we'd expect to find this electron in a specific location, whizzing around the nucleus like a tiny planet. However, quantum mechanics tells us that the electron doesn't have a definite location until we actually measure it. Instead, the electron exists in a superposition of all possible locations, a kind of blurry cloud of probability, with each point in the cloud representing a possible location for the electron. It's only when we make a measurement that the electron chooses a definite position, collapsing from this cloud of probability into a single point. This concept of superposition is not merely a mathematical quirk, it has been experimentally verified countless times. It's a fundamental aspect of the quantum world, one that challenges our classical intuition and forces us to embrace a new understanding of reality where uncertainty and probability reign supreme. Section 4. Wave-particle duality, the dual nature of matter. This section delves into one of the most intriguing and mind-bending concepts in the realm of quantum mechanics. Another cornerstone of quantum mechanics is the concept of wave-particle duality. This principle is not just a theoretical idea, but a fundamental aspect of how the universe operates at the smallest scales. This principle, which seems like something out of a science fiction novel, states that matter can exhibit both wave-like and particle-like properties. It's a concept that has fascinated and perplexed scientists for decades. In other words, the fundamental building blocks of matter, such as electrons and photons, can behave as both localized particles and spread-out waves, depending on the experimental setup. This duality is not just a quirk but a fundamental feature of the quantum world. This duality was first demonstrated in the famous double-slit experiment, a groundbreaking experiment that has been repeated and verified countless times. In this experiment, a beam of electrons or photons is fired at a barrier with two narrow slits. The setup is simple, yet the results are anything but. If these particles behaved solely as particles, we'd expect to see two distinct bands on a screen behind the slits, corresponding to the particles passing through each slit. This is what classical physics would predict. However, the reality is far more complex. The experiment reveals a much stranger result, an interference pattern, a series of bright and dark bands characteristic of waves interfering with each other. This pattern is not what we'd expect if the particles were simply passing through the slits like tiny bullets. This interference pattern suggests that the particles are somehow passing through both slits simultaneously, a phenomenon that defies our everyday understanding of how objects should behave. This pattern suggests that the particles are somehow passing through both slits simultaneously and interfering with themselves, just like waves spreading out from 2 points. It's as if each particle is exploring all possible paths simultaneously and interfering with themselves, just like waves spreading out from 2 points. This self-interference is a hallmark of wave behavior, yet it's being exhibited by particles. Wave-particle duality is one of the most profound and perplexing aspects of quantum mechanics. It forces us to rethink our understanding of the nature of reality itself. It challenges our classical intuition that things are either waves or particles, forcing us to accept that the subatomic world doesn't conform to our everyday experience. This duality is a key reason why quantum mechanics is so different from classical physics, forcing us to accept that the subatomic world doesn't conform to our everyday experience. The implications of wave-particle duality extend far beyond the laboratory, influencing our understanding of the universe at its most fundamental level. Section 5. The uncertainty principle, limits to our knowledge. If superposition and wave-particle duality weren't strange enough, quantum mechanics throws another curveball with the uncertainty principle. This principle challenges our classical intuitions and forces us to rethink the very nature of reality. This principle, formulated by Werner Heisenberg in 1927, states that there are fundamental limits to how precisely we can simultaneously know certain pairs of physical properties of a quantum particle. Heisenberg's insight was revolutionary, shaking the foundations of physics. One of the most famous examples of this principle is the relationship between a particle's position and momentum. These two properties are intrinsically linked in such a way that measuring one with high precision means the other becomes increasingly uncertain. Momentum is a measure of a particle's mass and velocity. In classical mechanics, we can measure both position and momentum with great accuracy, but in the quantum realm, this is no longer possible. The uncertainty principle states that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This isn't just a matter of technological limitations, it's a fundamental property of the universe. This is not due to any limitations of our measuring instruments, it's a fundamental limitation imposed by the very nature of quantum mechanics. Even with the most advanced technology, we cannot escape this inherent uncertainty. It's like trying to pinpoint the exact location and speed of a shimmering wave on the surface of a pond. The wave's position and motion are intertwined in such a way that precise measurement of one disturbs the other. The more you try to fix its position, the fuzzier its motion becomes. This analogy helps us grasp the elusive nature of quantum particles and the challenges we face in studying them. The uncertainty principle has profound implications for our understanding of the quantum world. It suggests that at a fundamental level, nature is probabilistic rather than deterministic. reshaping our view of reality. It tells us that there's an inherent fuzziness to reality at the quantum level, a fundamental limit to how much information we can extract from a quantum system. This fuzziness is not a flaw but a feature of the quantum world. It's a reminder that the act of measurement inevitably disturbs the system we're trying to observe. This disturbance is a key aspect of quantum mechanics, highlighting the complex interplay between observer and observed. As we continue to explore the quantum realm, the uncertainty principle remains a guiding concept, reminding us of the limits of our knowledge and the mysteries that still await discovery. Despite these limits, our quest for understanding drives us forward, pushing the boundaries of science and technology. The uncertainty principle, rather than being a roadblock, serves as a beacon, guiding us through the enigmatic landscape of quantum mechanics.